Hello and welcome back to the stream. So last week we started implementing structs. We're able to declare a struct like so, and then see it in the corresponding AST. And we're also able to create a corresponding object of that struct, like so. That's the wrong one. Object of that struct, which allocates the appropriate amount of storage for it. However, something curious about the grammar actually. This isn't like, if you have something like this isn't like a grammar rule for a struct declaration, which has a special place where you can declare a variable. This is the regular syntax for a variable or function declaration. We just omitted the name, right? So this actually is the same grammar production as this one. But instead of having like int here, we have struct foo and then all the members. This is part of the same syntax. Which means you can also do stuff like have a function that returns a struct. Except that apparently there's a separate rule that disallows it, but like grammatically this would be fine. But this means as a consequence is that when we want to create a struct object like so, we don't support that yet because we are parsing the same struct specifier, but we haven't given it a body. So this is what we need to work on today. For starters, and it's essentially the same definition as if we have like this struct foo in here is essentially like a forward declaration of that struct. Similar like this one. This one forward declares a function, and then this struct foo is a forward declaration of a struct. Except that, so something like that. If we omit the variable name. So what all that means is when we go into our compiler, where we pass a struct specifier, or what's it called? Struct specifier. We can omit the body in there. So this entire body is optional. Right. And what this means in practice is that we have not a member list, but an optional member list. Okay. If we're having members, then this is a definition. Otherwise, it is just a forward declaration. So only if we're having members is it actually a definition. And then, of course, we need to if we don't have one, like the member list now also needs to be optional. So this is essentially, let's just say it can be optional and store an optional. No, that doesn't work because we're storing it inline, so we need to have a separate flag. So if we don't provide the members, then we, yeah, okay, like so. And then essentially we can use the logic, we can use the fact whether or not it is a definition to distinguish between the two. So in this case, we're having members, so it is a definition, right? But here it's just a forward declaration. And then later, if we're lucky, the same system that will resolve forward declarations to their matching ones might just take care of this one. Okay. Yes, and what this means in the compiler is we don't need you here. Instead, let's use two overloads a little bit cleaner. So the other overload, if we don't have members, we do have a name, but we don't have members. Then we don't pass the members along, since we don't have any. We do have a name. Okay. And this is muscle memory for a different project where I'm starting a target with P, so now I type P and press enter. But this is not the wrong wrong target here. Okay. Let's see. Eventually we need to split the compiler because it takes a while. Yes, so invalid use of incomplete object type. True. This is now incomplete since it's just a declaration, but it has already gotten a definition. So we need to is complete object type. Yeah, like if the decal has a definition. So apparently we're not resolving that definition correctly. So what's up with that? Right, so we've got a struct decal foo, which is a definition, and then we've got a struct decal foo, which is not a definition, which is of course wrong. Yeah, so something's not picking up the correct definition here. Right here, this function that is meant to resolve our forward declarations doesn't work for structs. Right, because it requires that they have external linkage for some reason. Right. I don't know why we are only resolving forward definitions if they're external and not if they're like static functions. Although I do remember that we're not handling static function forward declarations anyway. But I don't want to get into that right now. So if we only have the handling, like structs don't really have a linkage, right? They're structs. They don't appear in the object file anyway. So we might as well give them external linkage. And then that one just works. It's a bit of a hack, I guess. Set linkage. No. What's it called? Set link. Ah, yeah, we do have set linkage impl. Right. So let's use inheriting constructors here, so we can go to code application, cton name types, and then here we set the linkage cloud linkage external, and now we might be able to resolve struct forward declarations correctly. I need to split the compiler into multiple translation units. It's not bad. Yes, so now we resolved those definitions correctly, which means, let me add a comment here, we need external linkage in order to trigger forward declaration resolution. And then we should be able to get you again. So now that one should work. Since we now have a definition, we will resolve that definition. We might resolve that too late. Yeah. We do resolve it, but we resolve that too late. By the time we're resolving forward declarations, we've already triggered the error. Right. So there are two potential fixes for that. One is we resolve it when we declare struct. We attempt to resolve it. That would be the nice fix. The second fix is we treat, instead of triggering a compiler error on an incomplete struct type, we are only triggering it later, right? So when we call an undefined external function, this is essentially a linker error. And apparently not. I was to say it will trigger a panic at runtime, but oh, right. Right. We do resolve that at the end. It doesn't matter. So apparently, so I thought we would only trigger that at runtime, and we could do the same thing right here. Defer the check for whether or not it's complete until we actually need this one, but apparently this isn't structured in that way. So when we need a struct decal, we need to look for a previous one. So we do have all these structs in a state somewhere. And instead of keeping them in a list, let's keep them in the symbol table. And then when we encounter something which isn't a definition, we look it up in the symbol table. Yes, that sounds like a plan. So what's the type of the symbol table here? It's a symbol table of as symbol to pointers. Right, symbol table C of as symbol to pointers to our structs. And then right here, instead of pushing it back, we do an insert or shadow. If it's a definition, we insert it. No, that one. Okay, so I need two separate. I need a list of all structs. Actually, no. So the reason the purpose of the struct member is that we keep a list of structs is previously they were only part of the they're only part of the type and don't actually appear in the AST. So we don't print them. So to print them, we just added them to the AST at the end. But we don't need to add struct forward declarations to the AST because they don't give us any more information than what's already available. So let's just insert them when we have a definition and not when we are having a forward declaration. So instead of struct, we're keeping that struct defs, so only the definitions. And then we want to collect them all into a list. Name def in state struct def structs and then we insert them right here. I might not provide an iterator for a symbol table. Apparently I do. So that's good. So now, right, that's only half the story. We of course then need to actually resolve them when we look it up right here. So return results. So we look for an existing struct definitions of that name. So auto def state struct defs look up name symbol. Result we set you to the definition. So now we resolve the struct definition. If we already encountered it lexically before, which means we are now crashing. Okay. Let me guess, you're null. So we've got a null pointer somewhere in. Oh, right. We don't actually have any members in our struct decal. Because we want the definition at that point. Only the definition has the appropriate members. Okay, and now that one works. So we're creating a rebel object of struct foo, which is the one defined right here. Now a couple of things to point out. Struct names are essentially global. which is a bit interesting. So if we're defining like a struct foo in here, I'm pretty sure that is still the... No, it isn't. It isn't global. It's still a different one. Dang it, I need to do proper lookup. So, but like I do have a symbol table somewhere, right? I can do like name lookup somewhere. If you have an expression, an identifier expression, this does name lookup, right? By looking through the scopes for the appropriate struct. But since they're having different names, right? Like, so this one, like, we can't just piggyback on the existing name lookup, because that one's fine, and we don't want to do lookup for just foo, because this will find this int and not that one. So we can't really piggyback on you, but we still need to catch stuff like that. So that's interesting. Right. I think I know what we can do. Like, we do lookup based on name, and we can give a struct the name struct space foo. This is never a valid name because the grammar doesn't allow it. So we can do then name lookup for struct space foo, like a literal space character inside the name, and do it that way. And yes, that one might work. But what this means is that I will now press undo a bunch of times, because I don't want the struct devs. I want the previous one where we're just having a list, and then I maybe should commit that. Right, that part. So that part still, so we just need to resolve them in the appropriate time. Pass struct forward declarations. They're not really forward declarations because, but never. No, it doesn't matter. Okay, so then we need to piggyback onto the symbol table thing. So first of all, let's... Right, so we've got insert new decal. So we also do name lookup for name. So decal name lookup at the current point, as symbol for name. Which we're using right here in the identifier expression. This thing is now name lookup. Right. Yeah, let's use name so we can have a location as well. Okay. Silo return decal. Okay. And then the identifier expression just uses u instead. Name lookup state name. If decal null pointer. Yeah, like we are not doing good on error recovery at the moment, so let's just return null pointer. This will crash at the other point, like somewhere in the parent, but that's okay. Okay, so now we can do name lookup also for struct decals, which was the point. So struct specifier. We want to add that to the list of structs, but also add that to the insert u into the symbol tables when we have a definition. We also want that when we have a declaration. This should be smart. Right? If we are like inserting a declaration, then that shadows the existing one, but like we don't get an error. Like you can have multiple declarations. We might override it incorrectly, so let's see. But now we can also do like I don't want to do like name lookup correctly. I want to do like I don't want to get an error for name lookup because it's fine if we don't have a definition yet. Unlike when we have an identifier expression where it is an error when we have that. So that's it. What this means is we have our struct specifier, and then like if we're having a definition, name lookup states name, then we want to set you to the definition. Set definition dev. Right. Let's see. Okay, now we got a bunch of errors because this one is bogus. Alright, but this is what I meant. This foo is not the same name as that foo. So we need to cheat a bit and don't like need to separately add something to the name. So if it's a struct decal, then we need to do something, otherwise we can just return the name of the declaration. But if it's a struct decal, I don't actually need the thing. Then we prepend like struct to it to get like a unique name. State that as symbols dot now decal name. So we get the C string. Auto struct name is like struct followed by the actual name to get something unique. And because of the space in there, this is guaranteed to be unique. And then we need to enter new. Symbols intern struct name length. And now instead of decal name, I need to say name. Right. Right, so. And now like the struct foo and the int foo will have different names, and we shouldn't get duplicate definitions for those. Yes. We still have like duplicate local definition of the struct foo, which is fine, since we have that. Right, and then we're crashing somewhere else. Okay. So why are we crashing now? think I know why we're crashing. Because when we do name lookup for the struct one, we don't want to do name lookup for the actual name, but we want name lookup for the struct name. So let's say bool is struct, and then add a function process get get struct name which does this logic. So given a name, it gives the struct name. If it's struct, so the symbol is, if it's a struct, we want the struct name instead. Otherwise, we can just use the name as is. Right, and then we do lookup for symbol. And then here we can also say simplify you. So if it's a struct, we want the struct name. Otherwise, we want the decal name. Right, so, okay. So now we just need to fix our call sites. Apparently, so here we're not looking for a struct, but when we actually do look for a struct, then we want a struct. Okay, like Boolean aren't nice at parameters, but like a lot of this code isn't nice, it's just functional. Should refactor a lot of it, but okay, we're crashing again. Let me guess, another null pointer. Yep, another null pointer. Apparently decal members. So apparently something's messed up here in CodeGen, which is a bit odd. Let me do something like that. So apparently this function doesn't work if you don't have any members or something. Let me just comment it out and see whether the previous code works. Don't like care about CodeGen at the moment. Love. You. Okay. Just get something. So we've got, yeah. So now we've got like two structs, one with A and one with C. And this one's just foo. Like we don't really know which one it is. But anyways, each struct has a definition now. Wait, no, why is that one a definition? That shouldn't be the case. Like that one. What's going on here? So apparently this one is still a definition, even though it actually isn't a definition. Which pretty sure that's what we're printing it. Right. Like we should print nothing because it definitely is not a definition. So who makes you a definition? Maybe resolve forward declarations? Oh, I'm pretty sure like if we set the definition to itself, right. Then we end up being a definition. Right here, and since we... So this one will always find itself. And not the other one. Yes. Now we're no longer a definition. Which means that probably this weird layout bug, like I'm not sure why it crashes if we don't have any members. That's not right. But okay. Right. So that works, and we are creating 16 bytes for our struct. Oh, right, because we're adding the extra one right here. 8 bytes for struct. And if we have a local struct here that contains a char, right, then we're having a duplicate local diff. What? One here and one here, but that one's fine. That one's not a... Right. That should be the logic. Yeah. No, never mind. Okay. So that one shouldn't be a duplicate definition. So, like we're inserting this one or shadowing an existing one in the symbol table, which means replacing the existing one. So if both have a definition, we have a duplicate definition. But no, if both are definitions, then we're having a duplicate definition. Then we're having a duplicate definition, right? Otherwise, we're having a duplicate forward declaration, which is perfectly fine. Okay. So that, right, that one should work. And now we can't really see because we round up the size to 8 anyway. So let's make you bigger. Right, this is now 16 bytes for foo object because it refers to the inner struct, like name lookup works properly. I know another what doesn't work is if we do something like that. Yeah, and now we're crashing again. And we're crashing because this foo will be resolved to that struct in the symbol table. Because when we having something in the symbol table that is a definition, and we're adding our own symbol, which has the same name but is just a declaration, we are overwriting the existing definition. But we want to keep the definition in the symbol table instead. So we know that the thing in the symbol table always refers to a definition if we're having one. Otherwise, the struct logic breaks. So else if the shadowed is a definition, and we aren't one, which is implied by above, but it doesn't matter. The struct code assumes that we keep definitions in the symbol table. So then we just insert it back. Symbols insert or shadow, name shadowed. Put the definition back into the symbol table. And this one should be Decal is the one we inserted above. So it's not the most efficient code, but it should work. So now we're keeping, like, definitions are sticky in that sense. And yes, that one still works. And even though we're having the external foo in there, that one's still fine. So, yes. What else? That should be, I think that's, let's commit that. Struct definitions. Okay. So, something that's a bit annoying is if we do something like that. Right, since we are dumping all these structs in the top level, right here, we don't know which foo right, this object is referring to. It would be nice if we were to add them like somewhere else so we can, like, they're not really part of the AST anyway. We're just dumping them there so we can inspect them for debugging purposes. But still, it would be nice if we could just maybe dump them associated to the declaration that they are part of. Or something. Right, so if we're having that's not really, since we're not keeping track of that. Yeah, okay. Let's not worry about, like, this is just for our debugging purposes anyways, and it has no real impact on anything. So it's not important. So let's move on to members. So we want to say object.a equals 11. Which requires two things. Like, we obviously need to pass this stuff here. But then we also need to build a symbol table for the members. And when we're building a symbol table, we can also detect stuff like that. Right? Currently, that's fine, since nothing cares about the names of the members anyway. So let's start with that. So we want to essentially create a new scope for these structs. Yeah. Yes. So while we do so compiler struct specifier. Right here, when we're having the members, we want to add them, like, essentially add them to a symbol table to the current scope. So we can add a current scope just for that. The scope of a struct declaration. Right here. So when we're parsing the symbols, well, not here, we don't have any symbols here. Scope s state current scope. What's the order of arguments? Kind parent. Scope struct. Current scope becomes s, and then we set it back. And now we can insert them all into the symbol table and get errors if they're duplicates, in principle. That's not going to work because, man, the compilation times are getting annoying. Right, first of all, declarations are not allowed in this scope. Why are we getting invalid? Right. If it's not like we do allow structs to contain stuff. So that could take care of that one. Why are we getting an invalid use of incomplete object type? Right, it's not incomplete. So first of all, you notice we're not getting any error for duplicate definition. This is because they are not actually definitions at the moment. We're only, we're allowing multiple forward declarations, and a member decl is not a definition. So we need to make that a definition. Right. I'm interested that we're not doing that for a parameter decl, which would work the same way. Probably something else sets that. I won't, if I keep getting into anything else that I see, we will never make progress. So duplicate local definition as expected, but why are we now getting invalid use of incomplete object type? What? Why? That's really weird. Oh, because we're inserting the decl into the struct itself. Yes. Let's do something like that. Okay. So we inserted the struct name into itself, and then we were unable to find the definition. Okay, so now we're checking for duplicate names. It's a bit unfortunate that we're getting rid of the hash table at this point, because when we later need to do member access, we still need to look for a member with that name. But since struct members aren't that many, we can just use the linear loop instead. Okay, so check for duplicate struct members. That one works. So let's move on to member access. So this is an expression of some kind. Where do we have this is a struct and union members. Right, the grammar is here at the top. So it's a postfix expression, dot followed by identifier. So let's add a new AST node for that. We've got subscript. No, we don't have subscript. We call maybe a function call expression, right? A member access expression class member access expression member access expression. Need to define the node kind. Member access expression. And so we've got the thing that we are accessing. Member access expression, this is the object, and then we've got as symbol, which is the name. This one is the object. This one is the object. We need to store a name, and then we need to get that name. This is the member name. Okay. That's the thing. Now we need to update the printing code. Member access expression, member access expression, which we also want to print specially. Const member access expression. Namely, we want to print the member name and the type of the member name, which should be the type of the expression. Okay. And then there's a bunch of other code. So for example, that deals with expressions. The type. Yeah. For example, member access, there are L values. So node has kind clove. Member access expression. There are also modifiables. And they do have an address. Yes. I'm not sure how they interact with register, and I don't want to find out at the moment. Are they static L values? Like, I guess if they probably inherit that. So if you do like of a global variable, that should also be static. Like I'm really like sometimes I use the namespace name and sometimes not. So this is static if the object is static. And let me be a bit more consistent within this function. I just like to be explicit here. Okay. They are definitely not null pointer constants. They can be named they can't be, because struct types cannot be constant expressions. They're definitely not arithmetic constants. Yes, okay. So that's the AST side. And then when we're parsing an expression, we want to like another postfix expression, which consists of DSL periods followed by an identifier. Not an identifier expression, do I? Right here. Identifier, and we don't want to allow reserved names. Okay. Then when we do the parsing code, so we need to add some sort of callback at the appropriate place. Right here, this is a function call. Let's do that afterwards. So we're getting an object, an up, and a clove name member name. And then we are creating a clove member access expression at that location with the appropriate type. Right. So at this point, we need to look up the thing for the struct. So for that, we need the type of the object. So object type. So we can query for that. This has to be a struct type, otherwise we're having an error. right node try cast, it's c-lab deckel type, object type. If you are not a deckel type, it's actually just not the deckel type, but also like a struct. Okay. So we need to get a corresponding struct deckel. Okay. So if you don't have a deckel type, then we don't have a struct either. Otherwise, we can downcast view. Okay, so if we don't have a struct type, then we are indexing something wrong. To do error. Let me guess, you want a const here? Yes, okay. So now we need to find the member of that name in that struct. Member, which means we iterate over all members of the struct. If we have one whose name matches our member name, then we return that. Otherwise, we return null pointer. Return member deckel. Okay. If we're not having a member, that is also an error. Otherwise, we can create a struct member expression by giving you the type, which is the type of the member, right? Because that's ultimately the type we're getting. Our object, and then like I wonder whether like we're currently storing the name of the member, but we could also store the pointer instead since we know it. This doesn't really make a difference, since what we ultimately care about is the offset, and that's one, like during CodeGen we need the offset, which we need to compute somehow anyway. So like we need to do like a different sort of loop over it, so that's fine. We can just store the name instead. Like since they're interned, like whether we are looking for a pointer in a list or look for an intern string, like that's totally fine. Okay. So that part should handle like the compiler front and stuff. And then we should just crash during CodeGen. Provided we actually trigger this code pass. Right. That is not the crash I expected. So we've got some null pointer in there. Right, we like need to look, we want the definition. And that is an error if you don't have one. Right, because we can't index it anyways. And let's shadow the definition part of a struct deckel. So it returns another struct deckel. Right. Right, and that's the assertion file I expected. So CodeGen, we're simply not handling it at the moment. So we've got like a call expression somewhere right here. Member access expression. We also need to CodeGen an L value. because it is an L value. Member access expression. So we need, first of all, we need to get the address of the object. So get the address. What are we doing? We are visiting this particular node, which should be on top of this, like, I'm pretty sure this version of visit. Oh no, we're not visiting a tree. So we need to get the get the thing on the stack. So get the address of the object on top of the stack. So codegen L value context builder expression object. So now we have that. Now we need to know the offset of our struct member, and like there is an instruction, I think, aggregate member right here of a builder. Like we need the index of the member and then the offsets of all members that came before. So vector of layout members need to iterate over all members of the object type. Member in. Since we're in codegen, we can assume that everything works correctly. So we know that we have a struct decal, which we can get from the decal type of the object type. So we can then iterate over all of those members. If member.name matches the member name that we're looking for, then we're done. Otherwise, we add the member layout of view, codegen layout of the member type to our container. And now we want to get the aggregate member. The member index is how many members we had before. Members.data, members.size. Like, we don't need to pass to that function all aggregate members that came after, since it doesn't care. And I'm pretty sure like we're doing the correct signature here. My language server died. Right, the pointer's on top of the stack, and then we're adding the offset to it. And this will leave the thing on the stack. What? Oh, right. We want the decal type, we want the decal of view, and then we want the definition of view. Which isn't like the easiest thing to do. Okay, apparently invalid member. Oh, right. Okay. So the function still needs the current one. Probably to do like some sort of alignment running. And then your members.size -1. Right, so we're creating... Right, that's interesting. So we're creating a struct, foo, which contains an int, and then we're setting that int. But since the struct consists only of a single int, what we're essentially doing is just we're creating an int, and then we're directly storing into it. So now we can print that one out and get 11. And if I do something like that, that one. Oh, well, almost. That's really, like, why are both 11? Like, that's all. Okay, so we are creating a local allocation of 16 bytes. Then we're pushing 11 and storing that into the thing. Then we're pushing 42, we're getting the address of our struct. We're getting the aggregate member at offset 8. Yes. We're dereferencing it, we're pushing it, and then we're storing into that. That is okay. To print, we're getting the address. Hang on, what are you doing? You're getting the address. Oh, yeah. No. Oh, okay. This is an artifact since we're discarding it. What we're printing is the local value at offset 0. That's fine. And then the other one, we're getting the address. We are getting aggregate member 8. And then I'm pretty sure that's a bug in Lauf somewhere. Since it does some sort of folding here, which it's not supposed to do. Like it should dereference it, not get the aggregate member. Can I get the definition, please? Hello. Alright, so this one adds an instruction, and then we're doing invalid constant folding. So we want to load something which is a local address. Like we're doing somehow ending up in load store local. Because on top of the stack is a local address. Which is not... Yeah, I'm pretty sure this is not our fault. This is a bug in Lauf that you need to debug separately. But in principle, yeah. Like in principle, this one works. It just... what happens if I do shenanigans like that? Yeah, right? Then it works. Like some constant folding in Lauf as well. Which like gets us the ignores offsets within or something. Yeah, so that part still works. Okay, I need to investigate that later. So this thing is a mess. So let's provide a convenient thing to the AST. That's my language. Okay, number access expression. We want the object type. Or rather not the object type, we want like the struct. We've got struct decal. We don't have that at that point. I can at least do that. Yeah, because like it could be union. Anyways, so which we'll then do nodecast decal type object type and then we can get the decal, like get the definition. Object type definition, something like that. Need to define you in a CPP file. Somewhere in here. And then we can use you during CodeGen to get to at least say expression object type definition which is a bit nicer. Yes. Okay, that's the happy case. Now there are a bunch of errors. Well, that we need to account for. So, struct member access. Oh, right. Right here. So, if we don't have a struct decal, or the struct decal doesn't have a definition, then we cannot index this thing. Let me just copy the agnostic and adjust. So cannot index this, not index, cannot do member access on this expression. Member access, and then let's just fatal. Oh, okay. And then, so if we don't have have the wrong type, then we cannot index it. The other error is we don't have the member. Unknown member in member access. Member name that symbol Z string state symbols right here, and this is also a partial error. And finally, like I'm pretty sure we can only index L values. Yeah. Oh, dang it. It's not necessarily always an L value. That's annoying. Okay. So now we can do something like int I.member equal 11 and get a compiler error because that's not a struct. Yes. And I can also do that. Unknown member. Okay. Add member access expression. Now, why is it annoying that we can index, we don't need L values? For example, we can have a function that just returns the struct. And then we can do int I equal to f dot a. Right, that's legal, but we are crashing. Why are we crashing? Like I'm assuming, oh, I'm crashing because of something different that's not implemented. We do not support structs in argument and return types at the moment. But the annoying thing about L values is that I wanted to demonstrate is when we do like the member access expression, we need a pointer. So here we are unconditionally getting a pointer, which we might not have. Right. But this is a whole other thing, like passing it to functional arguments, and something that we definitely need to tackle next time. Because the way they currently works is if you have a function f that takes an int and does something with it. Then what happens in the bytecode is this function f accepts one thing on the stack. But if we want to pass a struct foo onto the stack, like the stack in Clof is like in love is 64 bits each. And this struct contains two 64-bit ints, so it's to right. Right, this doesn't fit on the stack. Instead, we need to pass a pointer to a temporary object that we materialized, allocated storage for it, and so on. So we need to adjust the calling convention. And I also need to fix that bug that we're having, where we're having two objects, and then like when we read from them, it does invalid constant folding. Which, hang on, why are we crashing? Oh, because of gotcha. Right, this does invalid constant folding right here. So I need to debug that. But that's it for this week. Until then, see you next time.